Welcome to today's ACPMS seminar, and it's Paul Laubie who will present the talk on volume preservation of B-series methods from the operatic viewpoint. Thank you.
Thank you for inviting me to speak. And so I will start to speak about volume preservation of B-series method from the operatic point of view. And the title is maybe slightly misleading because we already know the theorem that says that we don't have any volume preserving B-series methods. So the goal is to prove this using some operatic tools. And also we can extend B-series methods by looking at aromatic B-series methods. And if we have time, maybe we will see that we can also understand those from an operatic point of view. Okay, so I will, I will write the plan. So first, I will introduce B-series and aromas. So this is the actual numerical analysis, and everything else is combinatorics and algebra. So then I will speak about combinatorics and species. After this, so it is in the title, so I will need to speak about algebras, about operads. So I will speak about operads, and I will also need some algebras. But the algebra we consider will be in the category of species. So, and then I will actually speak about the proof. So, which is quite simpler than the original proof. And of course, I should say, assuming the line is long enough. And if we have time, I will speak about the aromatic B-series and the aromatic complex. Aromatic complex. And I should also say that I will, so if I speak about this, I should also say that this is some Schmerian-Berg homology. Okay. So first, with B-series. So I will quickly introduce what are B-series. If you are familiar with B-series, well, you can just skip this part and rest a little bit. And if you are not, it can be useful. So I will take F from D to D, and we want to solve. So y dot will be f of y. Okay, and I will assume everything I need to assume on f because I don't even know what I need to assume. I don't do analysis. I mostly do algebra. And for this to mean something. Now, so where does the B-series come from? Well, we can compute something quite natural to compute would be the second derivative of y. And so the second derivative of y will be this. Okay, so f prime is the Jacobian of f. And so I apply the Jacobian on y dot. And so if I should maybe write this. So if I want to compute the third derivative of y, well, I just need to apply the chain rule. So now, so f second is binary. So I need two and 3 points. So I need to give it two vectors. And of course, it tells me that this is not the only part. I also have these parts of one box. And okay, if we want, we can continue this, but we already understand where the tree comes from, because here I can replace y dots by this expression. So I have this, which will be this f1, and this, oh, this is bad notation, should be this. Okay. Okay, this is a bit tedious to write down. So what we can do is we can forget the y's anyway. So the first one becomes f if I forget the y. The second one, it is f prime f. And the third one, it is f second on ff plus f prime on f prime on f. And now we can write this as trees. So here I have a tree with only one vertex. Here I have, so with rooted trees. Here I have a rooted tree. So this vertex is f. Here I have f prime, and I apply it on f. And here I have the formal sum of two trees. So I have the first one, which is this one. So the leaves are some f's. And here, since I have two child, it is f second plus, and here I have this f prime, f prime. Okay. And so with this notation, in fact, we defined a function that go from the former vector space spanned by trees to some vector field. Okay. And also the fact that we have some trees that appear is not some kind of miracle. So in fact, if we already know a bit about operads, it comes from the fact that if I have a manifold with a flat torsion-free connection, the flat torsion-free connection actually gives some so yeah, the structure of a pre-algebra over the vector field. And if we know a bit about pre-algebra, we know that pre-algebra are related to trees. Okay. And so now I can define big F of a tree. So, and I can say that this is F of, so it is a case derivative of F applied on F of the 1 dot F of the K with, okay, so here I need to say that the tree tau is equal to some roots. And then I have some child of the root. So this is to 1. It's okay. And so F that go from rooted trees. So we put a dot here. You understand why later. 2 was a vector field, or here I have just a function from RD to RD. So, okay. So now, if I have an ODE, if I have an ODE, and I want to solve it, and I have a numerical scheme, I can understand the numerical scheme as another ODE. And then, okay, so assume we have a numerical scheme to a numerical scheme. To solve the ODE, or to approximate the ODE, I should say. But I can understand it using using B series by saying that I have F tilde that will be equal to a sum over the rooted trees of some parameter h. So I want a formal power series. So this is the number of vertices of my tree on this one. Okay, so here I have a symmetry factor. So sigma. So this take a rooted tree, and it gives me a number. I have a coefficient that depend on the tree, and then I have one function. Okay, and so what it means is, okay, so here I said if we have a numerical scheme to solve the ODE, it is not true. So some numerical scheme to solve the ODE can be expressed this way, and those are entirely defined by this sequence of coefficients. So to each tree, it will give me a coefficient, which is b of the tree, and it allows me to get another function, and then the numerical scheme. I can understand the approached solution as the exact solution of the modified function. Okay. So this is a numerical scheme which is associated to a vector series. I will speak a little bit about aromas. Okay, so if I have a divergence, okay, if I have an ODE, so assume that if we assume that the ODE, the divergence of the vector field is 0, so it means the solution of the ODE preserves the volume. Then now I need to try to find a way to encode this at the level of the trees. And so what we do is the following. So I will say, okay. So if I have a tree like this, f of this, I already gave a formula, but I will give another one. So if I give some name on the edges, like this, and I will try to get the case coordinate of this. Well, I can write this as the sum of f k I j. So this is a case coordinate of the derivative of f along I and j times f I m times f m f j. Okay. And the sum is over I, j, and m. Okay. And this is indeed what we want it to be. The case coordinate of this one. So this is actually what we want. And now, what I will do is I will allow some loops in my tree. And to be precise, I will allow one and only one loop. So I will say that everything go, so in the trees, I will orient everything to the roots. And here, I'm okay with one loop in my tree. And I can still write this down, and it will give me, so okay, I should give name here, M, N, I, J, and it will give me, and so here I no longer, so here I need to take the coordinates. Here it will be the divergence of something. So I don't have coordinate, I just have a number. F. So if I start with, let's say J, so the derivative is in I. Look at I, the derivative are in M, N, and J. Then I have the coefficient in M and the coefficient in N. Okay. And we have something which is quite nice with this, because it allows us to write down an explicit formula for the derivative. And so we have that for the divergence, sorry. So divergence of f of tau will be equal to the sum of some aromas of f of the aromas. And so what are those aromas? A of tau is so those are the aromas obtained by looping the roots Okay, so here what do we have? So if I look at A of just the roots, it will be this. This is a divergence of f. So if I look at A of the second Bezier tree, I will have this. And also we have this one. And okay, I think you can guess the other one. And now I have a nice theorem of which was proved by a lot of person. So maybe I should widen them. So and it was also independently proved by Chartier. And so, the only volume preserving B-series method is the exact method. So what it means is, so a B-series method is a numerical scheme that in particular does not depend on the dimension. It is a kind of universal numerical scheme, like Wunsch-Hutta or Newton. So it means that I don't have a universal way to approximate an ODE such that the approximated solution will preserve the volume. Okay. And now the goal will be to show this theorem using well, some operads. So since I would like to use operads, so first, why do I want to use operads? Well, I want to use operads because we already saw that we have some trees. I did not speak much about B-series, but we have some composition of B-series that are really related to operads. So now I would like to use operad to understand the proof of this theorem, because in my mind the proof, both the two proofs are quite convoluted and are not proofs that I can easily understand. So here I need to speak a bit about species and combinatorics. And so the first species I will introduce is the species of rooted trees. So what I would say is let A be finite set. I can get T of A. So this is the set of rooted trees such as the rooted trees. So that A is a set of vertices. Okay, and what I will do is, so if I write it like this, I'm relying a little bit. So I will write it like this. Okay, so now by definition, if I want to be a bit fancy, I can say that RT is a functor that go from so this is a category of finite set with only bijections to sets. So we should not be afraid of this. This only means that to any finite set, I associate a set in a way that is compatible with bijection. So if A and B are in bijection, of course, I can replace the vertices of my tree by, so if A is the vertices of my tree, I can replace it by B because the bijection tells me how to do so, right? But we need a bijection. So if I only have an inclusion, then it doesn't work because the set of vertices will not exactly be the new set. And it cannot be a surjection because if it is a surjection, then I can have several vertices that are the same, which is not allowed here. So here, a bit by construction, I should say. So the vertex are labeled in a bijective way. The vertices. But I may want to label the vertices in another way. I may want to label the vertices however I want. So the idea is that I can define a new functor this way that take a set. It will also give me a set. And the way I will define it is to X, I will take the disjoint union of RT of 1 to n cross x to the power n. But the thing is here, I have two actions of the symmetry group. I have an action of the symmetry group here by exchanging the labels, and I have an action of the symmetry group here with x by exchanging the order of the coordinates. So I don't have this redundancy, so I will not take the Cartesian product. I will quotient by the diagonal action. And okay, it is not really important to understand this functor, but the idea which is really important is that so RT of A, so it gives me trees, well, rooted trees, like that. Vertices are bijectively. And now, if I look at f of RT applied to x, it will also give me rooted trees, but the vertices are non-bijectively labeled, just labeled. Okay. I don't know how to write this in a concise way. Yeah. So here it is bijectively labeled by A, and here it is just labeled by X. And so maybe now you understand why I denoted. And okay, so I will denote RT of something of X. I will denote f of RT of X. And now, hopefully, you understand why I used the notation RT with a dot here, because this is RT of the point. And so RT of the point is saying that I have my rooted trees that are bijectively labeled. And now I say, okay, I don't want them to be bijectively labeled, and I will label all of them by the point. And so if they all have the same label, they don't have any. Okay, perfect. And now, well, a natural question is what's the use of this? So if I look at this formula, I should say here that the union is over n, and this look like this formula. This look like to x, I give the sum, because the union is a sum, of some coefficient, we say RT n times x to the n. This look like this, right? And well, it look like this because it is exactly this. The idea is I have a for my Fourier series, but instead of having a for my variable, I have a set. And so a functor from Finn-Bisch to set, it's a way to give sets to any finite set. And we know that finite set to bijection are just integers, right? So this, if you don't know what a functor is, you should not be afraid because it is a sequence of sets. And on the nth set, you have an action of the symmetry group. Why do we have an action of the symmetry group? Here it is quite clear with this definition for the rotatrice, because here it is a world where everything is bijectively labeled. And so I can exchange the labels. And because of this, I will get an action of the symmetry group. So here for rotatrice, it is by exchanging the vertices. Right. Okay. So now algebra. Oh, maybe I should not write it because I already wrote it. But, now I will say that I will give a name to the object I've defined. So there's a functor from Spin to set. And if you're afraid with this, is equal to the set, to the set of sequence of sets. So A0, A1, and so on, such that we have an action of the symmetry group on AN. Or ON. Now that we have something like this, and I also already mentioned that this is almost like a formal Fourier series. So we can define the product and the composition. So this will be the product, and this will be the composition. Okay, so get A, B, two species. Oh, those are called species, by the way. I forgot to say it, I guess. So we defined, so I should say this is a property. So we have a unique species C, such that f of C is equal of f of A times f of B. And when I say this, I mean that, so f of A times f of B applied to X is exactly what we want it to be. So it is a Cartesian product of f of A with f of B. So this is f of A on X times f of B on X. And okay, so we have this. And we denote C to be equal to A times B. Okay. And the thing is, we have a formula for C. So the formula of C, we need to, so to write down the formula for C, we need to evaluate it on finite sets. And now we write the finite set with small letters. So on a finite set A, it is the disjunct union over I j equal to A of I times B of J. And so if you know about formal power series, this is exactly the same formula, except the disjunct union, well, the plus is a disjunct union, right? And the product is a Cartesian product. Okay. So same. So we have a unique D in the species, so that F A composed with F B is equal to F C. Sorry. And we denote D to be a circle. So here, if you know about formal power series, you can retrieve the formula. It is a bit more convoluted, and I won't write it here because it is, well, not useful, but it does exist. Okay. And so now we can define what we call an operad. Yes, just what we call an operad. Okay. So this is a monoidal object in okay. So for some person, this will be a very good definition because they will instantly understand it. And for others, it is a very bad definition. So what I'm saying is this is a monoidal object in the category of species with the composition. Because here, okay, I didn't say it, but of course the composition is associative. It is not commutative, but it will be associative because it is associative at the level of the functions. How do you say function? So what does that mean? It means that an operad P, so second definition, so this is a species together so we have an application gamma from P circle P to P, which is associative. So if you want to think about algebra, so here we replace species by vector spaces, and we replace the composition by the tensor product. And this is a definition of an algebra. If you want to think about monoids, you replace species by sets and the composition by the Cartesian product, and you get a monoid. So really the idea is that the definition of a monoidal object is a definition which is really categorical, and we can define it in any category with the setting that we want. Okay. And since I'm a bit slow, I will. Okay. I'm a bit sure that what I was thinking would be. So if there is question, do not hesitate to ask the question. Maybe you want an example of operad? And I will give one example of operad. I will give an example. So we already saw that we have a species that we all love, which is a species of rooted trees. And the idea is rooted trees is an operator. Okay, so I did not tell you what was the composition, so you have to trust me. You have to trust me that this on the set A, so this is the set of, so first I want P, a partition of A, so I want, this is P, tau, and a correction of tau I, if I with P, with P, a partition of A, tau, so tau is a tree, a rooted tree on P. So if I say on P, it means that the set of vertices is P. And tau I is a rooted tree on I. So since P is a partition of A, I is a subset of A. And so tau I is a small tree, such that the vertices are exactly I. So I can give an example of such an object. So I can have a small tree here. I will have elements of A inside the vertex, but I don't really want to write them down. So, and all of those trees are in a way that they give us a big tree. Yeah. So this will be an element of RT, circle RT of, so 1, 2, 3, 4, 5, 6, 7. Okay. I should not write it like this. Okay, so here I should give numbers inside the vertex, inside each vertices, but you understand it. Okay. And so now how can I make this into an operad? I can make this into an operad the following way. So what I will do is, if I have, so this, okay, I will write a smaller tree. I will send this to a formal sum where this guy at the bottom will be the, oh, okay, this one is a bit trivial, so okay. This one is a bit trivial. I should. So the idea is I will graft the trees one on top of the others. This plus, so I always have this small one here, but now maybe I can graft this here and this here. Or I can graft the other way around with and this one here. And I also can graft everything at the root. Okay. So now that we see that we have trees, we can guess then that operads will be an interesting object to work with for the purpose of the proof. Okay. So is there any question? Because here I write a little bit. So here, this is an operad, but you can see that I use plus signs because I'm not in sets, I'm in vector spaces. So I write a little bit, and if you go back at the definition of operad, you will need to replace everywhere where I put sets with vector spaces. But well, I don't want to give all the details because maybe it is a bit confusing. Okay. And the interesting thing about operads is that they encode algebraic structures. Okay, now what is an algebra with species? Okay, now I want to speak about Lie algebra. In species. Well, we know what a Lie algebra is, so I will record this. So a Lie algebra. So this is a vector space. It's a vector space V, a bracket equal to V into V to V, which is skew symmetric. Plus it satisfies the Jacobi identity. Well, a Lie algebra in species is a species S and a bracket Okay, so here I should say that this is a linear species because I work with vector spaces, but okay, this is not an issue. Which is, well, you guessed it, it needs to be skew symmetric and satisfies the Jacobi identity. Oh, I forgot. Okay, now that we have this, we can guess what we work with Lie theory in species. And well, the answer is everything that you can write will work. So you can think about Schreier-Heisenberg homology, you can think about universal enveloping algebra, you can think about everything. Okay. And now what I want to say is, I will give an example, which is RT, the species, is Lie algebra. In species. And how it is defined? Well, yes, I will denote brackets, and it will be an element of RT, and it will be 1, 2, minus 2, 1 in RT. And now I will say that the bracket of two trees, tau and gamma, this is this, and I will compose tau in 1, and then I will compose gamma in 2. And so I didn't tell you what it means, but it means that I take tau, I put it inside the ether 1, I put gamma, I put it inside the ether 2. It gives me an element of RT circle RT. And then I have a map that go from RT circle RT to RT. And so the answer is it will give me tau with gamma, which is grafted over tau, and the sum over all the vertices that I can graph gamma on tau, plus, minus gamma, and I graphed tau on top of it. And you can check everything. This is indeed a Lie bracket. Great. So I have something like 10 minutes, so I will introduce the objects that we need. Okay. So the object that we need, I already introduced one. So the first one object that we needed are the rooted trees. And we understand what we need the rooted trees because in the definition of Butcher series, we have rooted trees. And we also need another object. We need the aromas. So the aromas, I will define something new. I will okay, so I will quickly check the notation that I used. I will call it A for aromas. So A will be the species of aromas. So it means that A of a finite set, let's say I, is a set of aromas such that I is a set of vertex of vertices. Okay. And here we can see something which is really, really interesting is that if I have an aromas A, and if we grew a tree on A, this is still an aromas. So I will define something which is called the colored operads. So I didn't have time to introduce it, but species are for my Fourier series. I can understand for my Fourier series in several variables, and for my Fourier series in several variables will give me species with several variables, and we call those colored species. And so 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 these species have two colors. So it means that I have two possible kind of variables in inputs, and the output is one of the two kind of variables. Okay, so let's I don't remember. Okay, I will look a bit here. I don't remember the name I chose for the variables. So we have O and M, the two colors. Okay. And okay, why did I not tell like this? And so I need to define what is RTW of the set. So 1 to n, empty, and then I need to say what is the output color. So this is the color O, and this is the color M in inputs. So this will be rooted tree. Then I will say that RT of and here I will just put a singleton and color N. This is almost RT. This is so trees such as the oh, I should not need to tell this. So this is rooted trees that the roots is A and other vertices is the set 1 to 1. All right. And then I need a last one. So 1 it will be empty, but the output is M. And this will be A, the set of aromas. Okay. And so here, if we want to understand why we defined it this way, we need to go back to the last thing I wrote. So here I said, if I put an aroma and I graph a tree on top of it, it is still an aroma. So this set, this is the two color species, where the O input is anything, the M input is exactly one object, and the actual species is given by the trees, such that the M input is the root. And here, those are the one with the M, with an output being M. So it means that in the root, I will be able either to put a rooted tree such that the root is labeled by an M input or an aroma. And then if we remember how we defined the operad structure on the rooted tree, we understand that grafting a tree above an aroma is exactly composing an aroma, composing the aroma at the roots of the tree, of the small tree with 2 vertex, and the other tree in the leaf of this tree. So I will write it probably in a better way. So the idea is we have this. So this is in RTW of singleton 1, and then AB and A, and this is of color N. And here I can put, if I have A, an aroma, and T, a rooted tree, then I can define this. So here in A, I put the aroma, and in 1, I put the rooted tree. And it will give me something like this. It gives me an aroma, and I graph the rooted tree on top of it. And this is an aroma. So here, we have defined, okay, so we managed to define this operand. And I will quickly finish because I'm already a bit over time, I guess. So we have this that live inside RTW of singleton MTN. This is indeed an aroma, and the set of vertex is indeed singleton 1. And the idea is that this is a divergence. So we can put a tree inside this, and so we define this. So this is 1 composed in 1 with a tree. And this is the sum over A of something that we already wrote. This is the sum of the aromas that we get by attaching the root of T, of To, to one of its vertex. So this is the divergence. And we can do something else. What we can do is okay. So we also have the reduced divergence, which is given by I get my tree. So okay, so here T is in where T of something and T and O. And so if I take gamma inside RT of something singleton A and N, then here I can define gamma composing singleton A with this. And this will give me, okay, so this will give me, so I will have gamma and I will have a loop at the root of gamma. So here it is loop at the root of gamma. Now, if I want, okay, so I can compute the operation this composing something minus the something, and I compose in the root this. And this, I will say that this is if 0. And what we have is that the volume, preserving B-series method. Okay. Why are they giving by care of div0? Because if we look carefully at what div0 do, div0, it will loop the it will loop the root to a vertex, and then it will remove the trees that we obtained by looping the root on itself. Looping the root on itself is exactly the divergence of f that I defined at the very beginning. And so it will exactly give every single trees that are that give 0 when we compose them by the divergent under the hypothesis that the divergence of f is 0. And so if I can compute this, then then I win. And theorem, okay, we can compute. Well, we did compute. I should say what which result we obtained, but I guess I am over time, so I will stop there.
Thank you for this nice talk. I think we have a few minutes for questions or comments or remarks.
I hope there are some questions because
To yourself, hopefully. You can. No, it's okay. So please, is there anybody with a question or a comment? Okay. I would ask, so can you understand also other properties of B series through this sort of approach, operatic approach?
Yes, definitely. So the idea is since with B series we are not fixed, we don't fix the dimension in which we work with B series, and it is a result or an exercise that is well known that the elementary differential are linearly independent in this case. And because of this, a B series is exactly formal progressively just an element of the completed free Prairie algebra with one generator. And because of this, we can understand everything about B series in this language. So as an example, the composition of B series is exactly given by the composition of trees that I wrote earlier. So I don't know where I wrote it. Okay, so here, in fact, you recognize the composition of B series. So if I want to compose two B series, well, I will look at my tree, and I will put some. I will choose. So here I have a tree of with 3 vertex. In each vertex, I will put another tree, and then the coefficient that I will get in front of it will be the product of all the coefficients that appear. So here I recognize this, and there is another product on B series which come from the graft of 2 trees. So we can understand this product from the operatic point of view.
Also composition of B series?
I mean,
substitution.
Yes, exactly. Yeah. So this is a substitution.
Yeah.
So this one. And the composition will be with the grafting. So it's so well. I mean, we understand both products of B series with this language.
And what about the Lie butcher series? How would one think from this abstract perspective about the Lie butcher series?
Yes, we can. So I don't know much about Lie butcher series, but we can also understand them this way. So, so here it is given by the, okay, so I need to remember. Where was? So here it is given by the operad, which is, so I should say that this is known, well, what did I watch? So here it is a pre-operad. And we can also have a Lie butcher opera, which speak about Lie butcher series. I don't know much about this one, but it does exist, and we know some stuff about this. Yes.
Okay.
And maybe I should. I was hoping the question, and which is, so I said we did compute the kernel of D0, and I wanted to say that the actual result is that kernel of D0 is equal to E. What does it mean? It means that the E operand lives inside the pre-E operand. So here I said that this is a Lie bracket, and inside, in fact, it is exactly saying that. So I can see that see those trees are as operations, and what I'm saying is, if I have a space such that the operation are encoded by trees, then this commutator is always a Lie bracket. Those operations are not associative, but the commutator is still a Lie bracket. And so hence, volume preserving B series. So the vector space of volume, so V, so this is a vector space of volume preserving B series methods. So this gives me that it is the free algebra over one element, which is my field times my element. And so, and this is the exact scheme or multiple. Okay, so I was hoping this question. I didn't get it, so I asked it myself. So this is quite interesting because we exactly understand why only the exact scheme work, why the exact method work, because the vector, so the volume preserving B series method give a vector space, which is in fact a Lie algebra. And it is exactly a Lie algebra with one generator. And so, well, we know that the Lie algebra with one generator is quite trivial. But this also means that if I can have several B series methods and use different ones for different coefficients, then I will be able to have some volume preserving B series, but it will be given by Lie brackets of those volume preserving of the exact scheme for the coefficient. So it gives something which is slightly stronger. And the thing which is quite interesting is here we have a Lie algebra that appear. We have, in fact, the Lie operad that appear, but the Lie operad is a Lie algebra as an algebra of a species. And this allows us also to understand the aromatic B-series method. And you can classify all the volume-preserving aromatic B-series method by computing the Chevalier-Allenberg homology. In fact, the aromatic bicomplex is exactly the Chevalier-Allenberg complex of so what I'm saying is not totally right, but it is the Chevalier-Allenberg complex of these two-colored operad. Okay, we need to add something there. And because of this, well, we can compute this Chevalier-Allenberg homology, and it gives us a complete classification. It was already known, but well, we get another method.
Okay, thank you. Maybe any other question or comment or remark?
Yes, just a remark, maybe.
Hmm.
So you say indeed that if you have multiple colors, multiple vector fields, yes, you can reach volume preservation. And indeed, that's quite interesting since you actually can, and people develop volume preserving methods with splitting methods, and that's exactly what they do. Even if they do not rewrite it this way, that's exactly what they do. So just wanted to make that comment. Yeah.
Thank you. Any other comment or remark, maybe observation? Okay. If this is not the case, then let's thank the speaker again. Thank you. It was a very nice talk.
Thanks very much, Paul.
And then wish you a nice weekend and see you again in 2 weeks.
You.
Bye-bye.
Bye. Thank you very much.